Hi everyone, welcome to my YouTube channel Erudispace. I am Dr. Mohanty and today we'll discuss about the Otto cycle. So first, in the class Otto cycle, I'll tell you the mechanical cycle, then the thermodynamic cycle, and then the expression for the air standard efficiency of Otto cycle, and then what are the measures taken to improve the air standard efficiency of the Otto cycle. All these things we'll discuss in detail. So this Otto cycle is actually introduced by Nicholas Otto, a German engineer, in 1876. And all of us know that the cycles undergone by internal combustion engines are not cycles in true sense. And for that reason, the air standard cycles are perceived, and the air standard cycle uses air as a working substance and it undergoes the same processes as undergone by the actual engine, but it actually helps us to assess the performance of actual engines in comparison with the ideal engines. If you have any doubt related to the air standard cycles, you can refer to my lecture Introduction to Air Standard Cycle, where everything is well explained, the reason why the air standard cycles are perceived and what are the basic assumptions in air standard cycles. So I am not going to discuss those things in today's lecture. So first, what I will tell you is what is a mechanical cycle. The mechanical cycle actually consists of 6 processes. So the 6 processes of a mechanical cycle are 0, 1, next one is 1, 2, next one is 2, 3, next one is 3, 4, next one is 4, 1, and the last one is 1, 0. 0, 1 actually represents the suction, 1, 2 represents the compression, 2, 3 represents the combustion, 3, 4 represents the expansion, 4, 1 represents blow down, and 1, 0 represents the exhaust. Now let us discuss all the processes. 0, 1 actually represents the suction process in which the air-fuel mixture is injected into the system. 1, 2 represents the compression process. In the compression process, the charge which is drawn into the system during the suction is compressed to the clearance value. 2, 3 represents the combustion process. Just after the compression process is over, the spark plug gives spark. As a result, the compressed air fuel mixture undergoes combustion. 3, 4 represents the expansion. Due to huge amount of thermal and pressure energy developed, the expansion of the burnt air fuel mixture takes place, and that is represented by 3, 4. 4, 1 represents the blow down, where the pressure of the expanded gas is reduced to the atmospheric pressure, and 1, 0 represents the exhaust. As far as the air standard cycle is concerned, here we consider the pressure to be atmospheric when it comes to 0, 1 as well as 1, 0. But in actual case, some pressure gradient is to be maintained for the flow of the working substance into the system and from the system to the surrounding. But that is something that we'll ignore. Here we consider that it is drawn in at atmospheric pressure and the exhaust is also taking place at atmospheric pressure. But to draw finite amount of working substance into the system or to remove finite amount of working substance, you require infinite amount of time if the pressure remains same. But for the time being, you simply remember that both the induction, that is suction, as well as the exhaust is taking place at atmospheric pressure. Now, I will consider the thermodynamic cycle. The thermodynamic cycle is almost same as that of the mechanical cycle, but thermodynamic cycle doesn't consider the suction as well as the exhaust process. You can see the PV diagram here also. You can see the different processes, 1, 2, then 3, then 4. So the different thermodynamic processes are 1, 2, 2, 3, 3, 4, 4, 1. Deliberately I have introduced point 0 so that there will be no confusion when you compare the thermodynamic cycle with the mechanical cycle. In thermodynamic cycle, process 1, 2 represents the isentropic compression or reversible adiabatic compression process. This 1, 2 is reversible adiabatic or isentropic compression. You can represent this as isentropic compression. 2, 3 is constant volume heat addition. Three, 4 is isentropic expansion. And 4, 1 is constant volume heat rejection. So in 1, 2, what is happening? It is being compressed following a reversible adiabatic process, or it is an isentropic compression process. 2, 3, heat addition is taking place at constant volume, because all of us know that to ignite the charge in case of petrol engine, the spark plug gives and spark, and that spark is actually given instantaneously, so the volume remains almost constant, and you consider this to be a constant volume process. As far as 3, 4 is concerned, it is again an isentropic expansion or reversible adiabatic expansion process. 4, 1 is actually your constant volume heat rejection, because heat rejection takes place when it reaches the bottom dead center position. Now, if you compare the mechanical and the thermodynamic cycle, as far as the work done is concerned, always the area coming under the PV diagram represents the work transfer. So there is no difference, because 0, 1 and 1, 0 both are lines, so they do not consume any work, or they do not even develop any work. So As far as the work output is concerned, there should not be any confusion as regards to the PV diagram when you are considering the mechanical cycle as well as the thermodynamic cycle. Then, as far as the temperature entropy diagram of the Otto cycle is concerned, you can represent the TS diagram in this way. You have isentropic compression followed by constant volume heat addition, followed by isentropic expansion, followed by constant volume heat rejection. Let me redraw the PV diagram so as to provide space to calculate the air standard efficiency. So this is actually the PV diagram, the earlier diagram that we have drawn. It is isentropic compression followed by constant volume heat addition, followed by isentropic expansion, followed by constant volume heat rejection. Now, how we actually calculate the thermal efficiency? For that we need to consider the work and heat interactions, and here the compression process you are doing work, that is WC, and in the expansion process this is the work, that is uptake. This is the heat supplied, QS, and this is the heat rejected. You can calculate the thermal efficiency in terms of the work interaction as well as the heat interactions, but it is always convenient when two of the processes are isentropic processes. You can represent the air standard efficiency of Otto cycle in terms of heat interactions, because in two of the processes no heat interaction is actually taking place. So the efficiency will be heat supplied minus heat rejected divided by heat supplied. Now, what is QS? QS is mCV into T3 minus T2, where M represents the mass of the working substance, CV is the specific heat at constant volume, and T3 and T2 are the temperatures at the cardinal points 3 and 2. Similarly, the heat rejection is represented by 4,1. So this is mCV into T4 minus T1 divided by heat supplied, that is mCV into T3 minus T2. So this becomes 1 minus T4 minus T1 divided by T3 minus T2. So this is an expression for air standard efficiency of Otto cycle in terms of temperatures at cardinal points. Now, we will actually represent the efficiency in terms of compression ratio. So what is a compression ratio? Compression ratio is actually the ratio between the total cylinder volume to the clearance volume, and if we refer to this diagram, this one actually represents the total cylinder volume and 2 is the clearance volume. So compression ratio usually represented by R suffix K, H V1 divided by V2. That is also equal to the expansion ratio when it comes to your Otto cycle, that is equal to V4 by V3. So now we'll actually derive an expression for the air standard efficiency in terms of a compression ratio. I have actually eliminated the other diagrams so that we can do it and smoothly utilize the space that is provided in the whiteboard. And you do have the PV diagram, which is definitely essential to find out the air standard efficiency. Now, here what we'll do, first of all we'll consider the two isentropic processes to establish the relationship between the compression ratio and the different temperatures at cardinal points. First, let us consider the isentropic compression process 1-2. So for isentropic compression process 1-2, T2 by T1 is equal to V1 by V2 to the power gamma minus 1. And this is your equation 2. You can consider this to be equation 1, that is the expression for air standard efficiency in terms of temperatures at cardinal points. Now, for isentropic process 3-4, T3 by T4 is equal to V4 by V3 to the power gamma minus 1. But one thing that you can observe by referring to the PV diagram, that V1 is equal to V4 and V2 is equal to V3. Now, this V4 may be substituted by V1 and this V3 may be substituted by V2. So this becomes your equation 3. Now, from equation 2 and 3, we get T2 by T1 is equal to T3 by T4. This implies T4 by T1 is equal to T3 by T2. And if you deduct 1 from both left hand side and right hand side, you get it as T4 minus T1 by T1 is equal to T3 minus T2 by T1. And this implies T4 minus T1 divided by T3 minus T2. Here it is actually T2. Is equal to T1 by T2. So what is T1 by T2? T1 by T2 is equal to 1 upon T2 by T1. So what is T2 by T1? That is equal to 1 upon V1 by V2 to the power gamma minus 1. So this implies T4 minus T1 by T3 minus T2 is equal to 1 upon Rk to the power gamma minus 1. So that you can substitute, and eta Otto will be equal to 1 minus 1 by Rk to the power gamma minus 1. So this is the expression for the air standard efficiency of an Otto cycle in terms of compression ratio. The next thing that we are going to discuss is that how can we improve the efficiency of an air standard cycle. You can denote this as equation 4 and this as equation 5. So equation 1 and 5 represent two expressions for the air standard efficiency of an Otto cycle. The first one in terms of temperatures at the cardinal points, and the second one is in terms of the compression or expansion ratio. Now, obviously from this we can make out that we can improve the air standard efficiency of Otto cycle by increasing the compression ratio. But what is being observed that we will analyze. This is a plot between the efficiency of the Otto cycle and the compression ratio. So what is being observed? This is actually 1 where the compression ratio is 1. It actually steeply rises up to 8, and after that it actually flattens. For different ratios of specific hits, when it is suppose say 1.6 or 1.4 or 1.3, because the ratio of the specific hits is different for different substances. For monoatomic gas, for diatomic gas, that is different. But what is being observed, that when the compression ratio reaches a value of 8, after that, even if you increase the compression ratio, significant increase in the efficiency is not being observed. And there are certain other problems associated with very high compression ratio, because if the compression ratio is very high, it may result in engine knocking or detonation. And engine knocking and detonation is an abnormal combustion process, and that is not at all desirable. That may be eliminated by using tetraethyl lead, which was first introduced in 1920. But now what is being observed, that this tetraethyl lead is causing a lot of vehicular pollution, and in most of the advanced countries they have started phasing out the tetraethyl lead addition from 1975 onwards. So usually what this tetraethyl lead does when it comes to improving the performance, it reduces the engine knock, and usually 1 part in 900 parts of petrol is being added, but that is not being followed in most of the countries. There are few exceptions, like countries like Iraq, then Afghanistan, North Korea. There are few countries which are still using this, but it is not at all being used in most of the countries. Now, so for that reason, there is a limitation to which we can improve. You can increase the compression ratio to improve the efficiency. The next is this value of gamma. Higher the value of gamma, definitely this value will be lower, because this is there in the denominator. Particularly when it comes to the monoatomic gases, definitely as it is higher, this value becomes lower and efficiency is improved. But in most of the cases, we do use heavier molecules, and for that reason the air standard efficiency is reduced. So I sincerely believe that today's lecture on air standard efficiency of Otto cycle, where we have discussed everything related to this, right from the mechanical cycle, the thermodynamic cycle, also we have derived the expression from the first principle, would be extremely useful for all of you. You can follow the first principle and derive expressions for other standard cycles like diesel cycles and dual combustion cycles following the same principle. Thank you very much for being with me for so long. Hope to see you soon for another lecture on my channel Erudispace. But please don't forget to comment on this video, and if you are having Any doubt related to this, please do put questions so that I will try to answer.